Perfect,
Okay,
perfect.
it's okay. Okay, okay. Okay, good day to everyone. For me, it is an honor to be here. Thanks again to Marco, Marcelo, Brian, and all the community around SciTinyML-24. For me, this has been a very, very a good experience to share with the community of Tiny Machine Learning several years from the foundation of this network. For me, this is a very great experience. Thanks a lot to everyone to allow me to learn about this technology. Today, I want to share with you a general overview about artificial intelligence, machine learning, and specifically maybe deep learning, because uh, today the artificial intelligence have a lot of advance, and that advance is produced uh, essentially by deep learning. Okay, so this is my email. If you want later to contact me, your question, possible comments are very, very welcome to me. Okay. This is my I am my name is Jesus Alfonso Lopez. Let me put this. Okay, it's better. My name is Jesus Alfonso Lopez. I live in Colombia, in Cali. I'm an electrical engineer. I had a master and doctor in engineering. This is my LinkedIn profile if you want to contact me, okay? And here I said before, in Cali, Colombia. Colombia, this is a country in South America. This is Cali. Cali is a city in the southwest of Colombia, very near to Pacific Ocean. This is our campus, Universidad Autónoma Occidente in Cali. For me, it is very, very awesome to present our institution and to share with you everything about artificial intelligence, specific in tiny machine learning. Okay, we are beginning to the talk with this sentence. This sentence is in some point on the history was said by Isaac Newton. It's about the context is different. It's about the development of the physics, but for me is applied to the development of artificial intelligence, because a lot of people think the artificial intelligence is maybe a new technology, because a lot of people, you know, enter to the artificial intelligence world by ChatGPT. But ChatGPT and the end is only the last development of the history of artificial intelligence, and to get to ChatGPT is necessary, or what it was necessary to have a lot of developments. So to search ChatGPT, you need a lot of development. And one of my idea on this talk is that the people to show this kind of development. Okay, ChatGPT doesn't arise from the nothing; it's arise from the different development. Okay, in that sense, the current artificial intelligence is standing up with the shortage of a lot of the development before. Okay, okay. Initially, we are going to present a general definition about artificial intelligence, about machine learning. Okay, the modern artificial intelligence, the term was selected by John McCarthy in that famous Dartmouth Summer School on Artificial Intelligence in 1956. In that time, John McCarthy is a meeting with a lot of researchers about different areas, computer sciences, mathematician, etc., to try to imitate the general the biological intelligence. What is the short definition? Artificial intelligence is the field that try to imitate the biological intelligence. Okay, that is the idea. Imitate the intelligence that we can see in the nature, the human intelligence, but the animal intelligence too. And the history of artificial intelligence has several points of very, 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 a lot of development, a lot of points of less development in the history of artificial intelligence that's called AI winter. And now we are here in that kind of summer in artificial intelligence, but today no, it's not clear is the summer is continued for several years, or maybe in one time in one moment is going to decrease the summer, the temperature, and going to another winter, okay? But now we are here, that's kind of summer, and today there are a lot of development about artificial intelligence. So artificial intelligence is a very, very, very wide field. You have a lot of technologies. In this case, I try to show this kind of division. You have the general artificial intelligence, the field in general, and inside the field, you can find several subfields, okay? In our case, we are talking about machine learning. It's a subset or subfield of artificial intelligence. And inside of machine learning, you can find deep learning, okay? So we are talking about initially about machine learning. Machine learning today is very, very important. It's a technology that is very useful because you have a lot of data. A data in different situations. Indeed, in this talk, we are generating data. You know, with interaction in the Zoom, the video, the recording in this talk, you have a lot of data. And the idea is to take advantage of that data. And one of the way to take advantage is using machine learning, okay? And the machine learning allows to you learn using that data, okay? And if you have data, you can use machine learning, okay? But you can maybe think, what is the difference maybe with the traditional, you know, way to programming in this kind of, to take a picture of the data with machine learning, okay? For example, if you try to do this kind of application, you need to classify it. If in an image there is a dog and a cat, you have the data. You can go to internet and to find a lot of data. You can take your pictures, and you at the end picture of dogs, a picture of cats. And if you need to algorithm or a software that answer the question is if the image there is a dog or a cat, you can do this application in two ways. One way is you need to program in the rules. Okay, you need to find the model in machine learning, in general artificial intelligence. Use the word model. The model at the end is a kind of representation of a reality. In this case, if you need to represent the reality to classify if in an image there is a dog or a cat, you need to describe the rules, okay? To describe the algorithms, the different situation to find in an image a dog or a cat. But if you describe the model by yourself, and the end this process is manual. You need to find the algorithm. But using machine learning, you can automatize this process. You only need data. You need the images of dogs, images of cats. Introduce this data to the algorithms, to machine learning algorithms. The algorithm has an initial model. The model has some parameters to, you know, to find, to tune in, and the algorithm, in automatic way, finds the parameters to allow to you to find if in the image there is a dot or a cat. That is the magic of machine learning, because in this situation, you need to create the algorithm from scratch. In this case, the algorithms arise in automatic way, okay? You need, a kind of template. The template is the machine learning algorithm, neural network, k-means, the different algorithms. But the learning process find the parameters that the algorithm needs to manipulate the data. That is the magic. All the machine learning models follow the same, the same idea. ChatGPT, for example, is at the end, you need to train the ChatGPT using a lot of text. And the end, using a lot of text, trillion of text, this algorithm find the parameters of the language models to produce the answer to a different, prompt that you can enter to ChatGPT. Okay, that is the magic. Use the data to find the parameters of your model. Okay. What kind of data you can use to this kind of algorithms? Initially, we can use structured data or tabulated data. For example, if you have a traditional data set, you have this kind of data, okay? For example, it's kind of in this case is the information of some information about people in a bank. And the end, you can use this information to, for example, find is a good person to get a credit, for example. Okay, you this kind of data is structured data, but you have a lot of data. For example, you have images. Images is a kind of not structured data. Images, you have the language, spoken and written language, and in this kind of data is use normally is complicated to process. Okay, but the latest techniques or artificial intelligence can't manipulate this kind of data. That's easy, a big advantage, because now a lot of the development about artificial intelligence is about using data, using images, using language, and so on. Okay, so in that way we can arrive to deep learning, because in this, this kind of world, if artificial intelligence is that kind of world, you have different, countries in this world. One country or one continent is machine learning, and inside this continent you have deep learning. Okay, and deep learning is very useful to manipulate this kind of data, images, and language. Okay, so I'm going to present a little overview about deep learning, to at the end understand how the learning produce this kind of development. Okay, that produce this kind of products, for example, ChatGPT and others. Okay, what is deep learning? The deep learning, and the very basic definition, is the traditional artificial neural networks. Okay, this is a kind of new name, but inside, deep learning is a new way to understand the traditional artificial neural networks. So what is the idea? The artificial neural network is try to imitate the brain. Okay, so if you try to imitate the brain, you have different ways to imitate the brain. You can try to imitate the logic of the brain, but you can try to imitate the you know the the components on the brains. In this case, the neurons. Okay, that is the approach that the deep learning try to follow. Okay, you have the biological neurons, and at the end you imitate one biological neurons in a very simple way, and you connect these artificial neurons and you create an artificial neural network. Okay, and at the end, if you have a lot of connection, a lot of artificial neurons, you have a deep neural network. Okay, that is the idea. It's a kind of bottom-up approach. You begin from the simple components, and you hope that you at the end have, the imitation of all the system. Okay. Okay. In the development of deep learning, you have several, points in the history of deep learning. Okay, first in 1943, McClure Pitts, they created the concept of artificial neuron. Okay, this model is very simple. You can see in this picture. At the end, you have some pictures, some inputs. Excuse me. You have the weights. The weights try to imitate the synapses of the biological neurons. You have the input, the weights. You multiply the input by the weights. And the end, you add all information. You pass for activation function and the output. Okay, the model artificial neuron is very simple at the end. Okay, but in the initial model, you can. There is a microphone open. Okay, thank you. At the end, this is the original model, but what is the problem? You need to find the weight, okay? Later in 1957, Rosenblatt produced his famous network, the perceptron, okay? The perceptron is a real neural network because you can train the weights, okay? You have an algorithm to find the weights, okay? In that moment, was very famous because even in some news on that ages, you can find similar news as today, okay? In a few years, we have artificial intelligence algorithm that it can be fixed similar to the human, something like that, okay? But these approaches produce the dense ledgers, okay? This ledger, maybe in the historic point of view, it was maybe the first, kind of neuron that is possible to use in different architectures, okay? Even today, you continue using dense ledgers, but with the union with another ledgers, okay? For example, what kind of neural ledger you can find in deep learning? For example, convolutional ledgers. The origins of convolutional ledger you can find in the neocognitron, okay, for Kuniigo Fukushima in 1979. He produced a model to try to imitate the visual visual, neurons of the brain, okay? And later, using this kind of architectures, okay, this is at the end, this is the the beginning of the convolutional neural networks. Jean LeCunte generated his famous model of convolutional ledger, okay, the LNet5. Okay? For example, you can see maybe a short video. This is a demo that time, and you can see the the number recognition of this kind of neural network in 1989, okay? The model can see the numbers, can recognize the different numbers. It's very nice. So, convolutional neural networks are very important in the history of deep learning and even in the history today in artificial intelligence because 20 years ago produced the famous ImageNet moment, okay? Because ImageNet is a very famous data set of images, and the idea is to use these data sets to create a classifier to classify 1,000 classes. Okay, so in 2012, AlexNet, a convolutional neural network, produced a very good results in these data sets. And when the people realize what is the architecture behind AlexNet, they find the architecture, it was based in convolutional neural networks. And in this moment, all the people began to use this kind of architecture. And through the years, okay, in ImageNet, the error begin to decrease, but the number of layers began to increase, okay? even in this year, the behavior of a convolutional neural network is in this data set, the performance is better than the average performance in this data set. This is a general overview of convolutional neural network. You have the input and the different convolutional layer try to do the feature extraction. And the end, you using that fixture, you enter those fixtures to the classification layer and to produce the final output, okay? You can use convolutional layers in classification, talking about images, okay? You can use convolutional layers in classification, in detection, segmentation, and so on, okay? But images and another kind of data are static on the time. So we need some kind of architecture to manipulate sequences data, okay? Data, at the end, a lot of the data depends on the time, okay? One of the first architecture to manipulate this kind of information, it was the Hotfield neural network in 1982. This is a kind of recurrent layers. Recurrent layers is a specific kind of networks that have these neurons have this kind of memory. The special ingredients of recurrent net layers are the memory. Okay, these neurons use the last output, and to use the last output, the neuron needs to memorize the last output to as input and to generate the next outputs. And then you have a kind of loop, and these recurrent networks can generate sequential data, okay? Another architecture is the famous LSTM in 1997, okay? This is a improvement of the traditional recurrent units, okay? But in what fields you can use recurrent layers? You can use recurrent layers in forecasting. You can use recurrent layers in classification. In the inputs are sequential data, okay? For example, these time series, the different, types. For example, the time series from the measure of the environmental variables, the time series, the measure of, accelerometers, and so on, okay? But one of the main application of the recurrent layers was natural language processing, okay? And for example, you can classify, the text. This is a text, and you need to classify the emotion of the text. You need to do that kind of translation, a lot of application, natural language processing, okay? So you have, this is the general pipeline to the language model. The idea is to enter to the language model. In this history of the learning, we are in the time of the language model. And this is the general pipeline. You have the text. You need to standardize the text. You need to do the tokenization. And the tokenization is to split the text in different, components. You need to assign index to each token, and this, at the end, this index, you need to generate a vector, okay? It's only the preprocessing of the information to enter to the model, okay? And you had a vector, and this vector at the end are the information that the model is using to process the text, okay? When you manipulate text with the learning, it's different to manipulate images, because the images are numbers, okay? The images at the end are matrices, and you have the numbers in that matrices. But in the text, you have, this kind of information. You have linguistic information. So you need to transform this information to a kind of information that the neural network can manipulate. For example, this kind of vector, okay? In this visualization, we can see a very famous embedding. That is the name to convert, the original sentence to vector is the name of that process is, embedding, okay? So in this case, this is a very famous embedding project. Embedding, this is the embedding produced by the word to vec. Each point here is a word, okay? The original vocabulary is about 10,000 words. And when do you try to produce with this kind of representation? Okay, first you need a vector with less, a dimension, because the initial dimension before to embedding usually is very large. You need vector with less dimension and less dimension, and you need to kind of, in the embedding to produce vector with its a feature. If a word is similar to another word, the vector must be similar, okay? For example, you find here the word dog, for example. Okay, you can see the word here, and you can see the another words similar that are closer to the vector dog, okay? You can find cat, okay, pet, something like that, okay? And the end, the embedding produce vectors, but the word with similar context produce similar vectors, and vector with less dimension, okay? That is the idea to embedding. So that vector are entered to the model, okay? Initially, the model is based in recalling ledgers, okay? We are talking about 2014, 2015, something like that, okay? So the traditional structure was this kind of structure. You had an encoder and decoder structure, okay? In the encoder part, you receive the enter the enter to the model, sequences to enter to the model, and you produce a sequence to output, okay? This kind of application, usually you can call sequence to sequence application. You receive a sequence, for example, the text in a language, that you produce another sequence, the text in another language, okay? But this kind of recurrent neural networks, it was used to this kind of application, language application, okay? But this is the traditional way to do that, okay? You have the encoder, okay? Remember, the recurrent network is a kind of or unit that begin to process the input sequence step by step, and the end produce an output, okay? This output is entered to the decoder part to produce the final output sequences. But you had a lot of intermediate states, okay? With each time of the sequences, each point of the sequences, you have information. And what happens if you use all the information? That is the next, development in this kind of models. You need the concept of adaptation, okay? What happened? You have the intermediate states, okay? The memory, because remember, the recurrent network is processing the sequence step by steps, and each steps you can produce a intermediate output. And if you add in the decoder part and attention decoder, you can do that. This attention decoder, yeah, in the traditional approach, you only use the last state, but in the attention decoder, you can use all the different states. And the attention decoder needs to find the states more important. How can you do that? Using the attention mechanisms, okay? The attention mechanism at the end is a way to compare, okay, the information that the decoder has with the information that different states. The comparison is a vector comparison, and the more similar vector is the vector that you need to put attention. That is the idea of the attention. Find the information that is more important to process in the decoder part. And the way to find the more important information is the usually is called attention. Okay, and these produce kind of results when you try to translate a one sentence to one language to another one. This attention can find this kind of behavior because the traditional translation usually is did word by word. Per word produce the word in the in the second language. Second word in the first language produce the word in the second language. But if you have that kind of structure different in the language, you can produce that kind of error. But this mechanism can find this kind of structure because some languages, for example, in English, usually you have the adjective before to the noun before the nouns, and in Spanish or another language you have the adjective after the nouns. Adaptation is can define these relationships and produce the right answer to the translation. Okay, and what is the evolution of the adaptation? The self adaptation, and the self adaptation is the main mechanism of the transformers. Okay, in the beginning on the end of the 2017, uh, was published this paper, Attention is all you need. It's a very, very, very important paper. It's a seminal paper because in this paper was described for the first time the transformer architecture, okay? So you have another layer, the self-adaptation layer. The self-adaptation layer is the main, you know, uh, component of the transformers, okay? And this is the equation, is very famous equation that is the self equation. You have another component, the Q's, the queries, key and values, and the end these are some matrices that you can to train to find the right answer to your transformer, okay? You have this kind of deep learning solve, you have different architectures, different layers with different applications. So today we have at the end a kind of transformed world. A lot of application, the more important application today, artificial intelligence, are produced by transformers, okay? So this is the transformers, the famous paper, the seminal paper, Attention is all you need. And you can find this figure. You have the decoder. It's similar. You can see the transformer at the end use the similar approaches to language that recurrent neural network. Okay, you have the decoder part and encoder part. Okay, and you have a lot of components inside. Okay, when you see the components of the transformers, you can realize at the end, you can find the different, evolution of the deep learning. For example, you can find dense layer, the first, layer that the evolution of the learning was produced, you can find in the transformers, okay? A dense layer. You can find, for example, some components that was origin in the convolutional neural network, for example, the normalization and the residual connection. The residual connection, it was proposed for the first time in a convolutional neural network, okay? You have, for example, the embeddings. The idea of the embedding comes from the traditional, for saying in some way, natural language processing that by using in the recurrent neural network, okay? And you have obviously the multi-hit adaptation, that this is the last component of deep learning. And the end, in this architecture, you can find all the history of the deep learning, okay? For that reason, to produce those transformers, the transformers source for the addition, the different developments in the history of deep learning, okay? You have these layers, residual connection, and so on, okay? In this visualization, a very nice visualization, you can see, a transformer. Okay, this is the traditional transformers, and you can see the inner composition of the transformer. You can use this kind of visualization. Okay, for example, this you can find aquí several models, but you have here the tokens. The tokens is the traditional way to split the text for a language model. You have the embeddings, the embedding token, the positional embedding is another operation that you need to do in transformers, and you have here all the matrices. Okay, you have the query weights, the carry weights, the query weights, the key weights, the value weights, and so on. Okay, you have all the structure here. It's very nice when you see this kind of visualization because you can understand in a better way how the information is, you know, uh, is is in the neural network. Okay, so the transformers, what the paper was published in the end on the 2017, and in the 2018 began to appear a lot of uh, models using transformers. Okay, initially the model of using transformers was the language model. Okay, you had the end different approaches to use a transformers as a language model. You can use a transformer, for example, only the encoder part. Okay, you can generate a language model using the decoder part, or even using the encoder or decoder. Okay, for example, if you use already the encoder part, you have this kind of architecture, for example, like BERT, Roberta, and so on. In the decoder part, you use it if you only use the decoder part to your language model, you have the GPT family, okay? And another model use the all the architecture, okay? In a very quick, review of the different models. For example, you have BERT. This is the paper of BERT. Only only to reference, I put the paper and the link. The idea is to share this, these slides, this presentation, and then you can follow all the information. Okay, this is BERT. BERT only use the encoder part. Okay, GPT use the decoder part. GPT is the ancestor of the ChatGPT. Okay, GPT okay, the GPT is a acronymus and is generative pre-training transformers. Okay, and you have a lot of language model, okay? Palm, Blabla de Google, you have Gemini de Google, you have this kind of model as ChatGPT, okay? All these models are based on transformers, okay? Llama is very interesting because it's open source, very, very nice for that reasons. But the transformers not only are using in language model, okay? But the original, application of transformers are the language, okay? But in this paper, Visual Transformers, some people on Google show that it's possible to use transformers to manipulate images. It's very nice because if you can use transformers to manipulate images, you can use all the potential of this architecture, okay? What is the trick to use transformers to manipulate images? And the end, the transformers was designed to manipulate sequences, okay? So you need to convert the image in a sequence. That is the trick. You have the image, you split the image in several patches, and using those patches, you create a sequence, okay? And then the sequence are numbers, okay? The transformer see vectors, okay? The vectors come from images or come from language. When the vectors come from language, is the traditional embeddings, but in this case, the vector comes from the pixel of the images, okay? And then you have these sequences, and using this sequence, you can use the transformer to manipulate the image. It's very nice. And the end, this approach works very well, okay? And you have the ingredients to the generative, the image generation, okay? Because you can encoder the traditional text using a transformer, okay? You can encoder the images using a transformers, and then you have a new representation, a vector representation of the images and vector representation of the text, and you need to, and then you need to find the right representation from a text to create your image. That's the idea. For example, you need to create a new image. You enter the prompt, the text. The text is converted to a new representation, a vector representation, and the image generation finds the correct image representation in this language, in this point, okay? You have, in this case, using this a kind of violet color, something like that, is the representation of the text. This green color representation of the images, and you have a vector representation. You need to find what is the similar representation in the image vectors, okay? And you have the representation, you can generate the image using an image generation. That is the idea, all the image generation that you have to date, okay? For example, DALL-E, this is the the way to work of DALL-E. You have the text prompt, you find using a transformers a new representation using a new vectors. Okay, this is this representation is called latent representation. You have the text, a transformers. You have new vectors in the text domain. Using another transformers, you can find the equivalent representation in the image representation, the vector representation of the image, and you have the image representation on the image in these vectors. You can use image generation. In today, the more useful image generation is based on diffusion model. Okay, that's the idea. The component and the end very important to this kind of generation again are the transformers. Okay, a transformers to create a new representation of the text, a transformers to find the representation of the image vector, and the end an image generator. Okay, Imagen is the model of Google. The behavior is and the end similar. You have again text from transformers to find the vector representation on the on the text space, and use in this case to find a diffusion mechanism to find the image representation to find to generate the image. Okay, this is stable diffusion. Again, you have the text prompt, you have a text encoder to find a text representation, and using a diffusion mechanism, you find the image representation. Okay, and using an image generation, you can at the end generate the image. Okay, but the transforming is not only used to text, no, to text and images. You can use transformers to generate another information. For example, sounds. Okay, you can use this is DALL-E, another model to generate sound using transformers. Okay, music LM, another architecture to generate, in this case, music. And you can even generate video using, for example, Sora. Sora, this is a kind of model, very, very, a lot of very information about, very news about Sora, okay? Because it's very, very impressive model, okay? And you have the generative artificial intelligence, okay? You can generate text, you can generate images, you can generate code, you can generate video, and so on, okay? But one of the main, components of all this architecture are the transformers. That is a kind of transformer too, okay? You have this is the different model based on transformers through the years, okay? You have here, for example, in 2018, the original Transformers, and the end is in if you want to be exact, is end on the 2017, okay? You have GPT, you have BERT, And through the years, you have a lot of the models, a model based on transformers, images models, models to language, and other kind of models, okay? And this is a kind of transformer solved by the open source, okay? In the community on artificial intelligence, when appears GPT-3, okay, there is a lot of concerns because all the new architectures begin to be closed, okay? So unfortunately, later appears Llama on all the open source model, okay? But at the end, to finish the talk, the tiny and the large meet together. Okay? Similar to the previous talk, we have several ideas in common, okay? In common, because you have the large language model and you have our word, okay? The tiny machine learning model, okay? So at the end, if you see the cycle of artificial intelligence in the last year, you can find here the HEI. You know, tiny machine learning at the end is a subset of HEI, and you have in this case generative AI. Okay, in this spectrum of application artificial intelligence, HEI and generative AI are very have techniques with a lot of potential. Okay. You had this emerging technology the last year, okay? You have again generative AI and HCI, okay? And this is the impact radar for generative AI in this year. You can find here the embedded generative AI, okay? It's a tendency in the generative radar to implement generative artificial intelligence in embedded devices, okay, in the edge and the tiny machine learning in general, okay. So, in tiny machine learning in HGI, we had a lot of experience try to optimize the model to use in these tiny devices, okay. And today, all this, knowledge about the model quantization is using to optimize the large language model, okay? As the previous talk said, you use quantization, pruning, value distillation, and so on, okay? But at the end, the first application of that techniques was in tiny machine learning. But today, that techniques are applied in, to optimize this model, okay? But in my opinion, I think that the new algorithms in model optimization that is applied to language model can be used in tiny machine learning. Okay, this is a kind of cross fertilization. Tiny machine learning produce techniques to optimize large language models, and the large language models, the new optimization techniques can apply in tiny machine learning. Okay, that is the idea. Okay, and at the previous talks said, today you can have a generative AI on the edge. Okay, for example, in this kind of mobile devices. Okay, for example, you can have a generative images in your phone. You can have a this kind of chatbot in your phone. Okay, but even using this ecosystem of open source models, you can have, for example, Llama 4 Micro in this kind of devices. You can have, for example, Llama and Raspberry, as I said before. Okay. Thanks. This is the talk. Thank you very much.
Thank you so much, Jesus. Let me congratulate on behalf of all the participants. That was extremely interesting. And as Marcelo said in the chat, 70 years of AI in 60 minutes. So that's really interesting to see the evolution. I think it was really excellent.
Thank you so much.
So let's see if we have any questions in the next few minutes. I'm sure there was one from Netu, which was asking, is transformer used for regression problems?
Transformers for what problems?
For regression?
regression problems. Okay,
Yeah.
regression. This kind of first cap, something like that. In my case, I use transformers in kind of regression problem using forest casting, for example. What is my experience? Okay, if you need to use a machine learning model for this kind of application for casting, for example, you need to prove different models, okay? In my case, depends on the time series. It's very useful to use, for example, XGBoost. XGBoost is a machine learning algorithm very powerful to manipulate time series data to do forecasting. But if you have a very complicated, time series, you can use transformers, and even the transformer can have better performance than other algorithms. In some, work that in my case, with a PhD student, we're working in forecasting using different, approaches and data series from, energy demand. And this time series is very complex. And in this case, what we use transforming, and the results are very good, okay? Depend on the application, but it's possible, and then it's very possible.
Good. We have one question from Amied, please.
Yes, thank you.
Thank
if you have any paper about using transformers in time series, this would be very interesting for me.
Very interesting.
Regarding RNN with time series, it's not useful because of the vanishing gradient problem. But I don't know whether one uses still now RNN with LLM. Probably it is, because you have shown in your slides you are using RNN with LLM. But with time series, one usually uses LSTM.
Yes.
At the time being, RNN is end.
Yes, you're right. You're right. No, thank you so much. Thank you for the comments. Okay, in my case, in the presentation, I use RNN as general representation of the recurrent neural network. Okay, because the vanilla recurrent networks, LSTM, GRU, and so on, all recurrent neural networks. Okay, but okay, thank you for the comment. Maybe I need to specify that in this case is all the architecture that you can call recurrent neural network. For example, STM, GRU, and so on. Okay. In our case, we're using LSTM, GRU, and transformers to manipulate, to do forecasting on time series, and it's very nice. Depends of the time series, you can have better result using, for example, a transformer. It's possible.
Excellent. Any other comments for Professor Jesus? No more questions. Then thank you very much again. That was very interesting. And
excuse me, Pedro Gonzalez is a question.
Yes. So
what will you say the flaws or limitations of transformers? Okay, this is a lot of people is working on that because for example, what is the reality? The transformers should be a very robust architecture, okay? Because even the initial idea of transformers is, and the end is using today, okay? But for example, in my case, in my opinion, some point to improve maybe is the size of the matrices, because at the end transformers are very big in general, okay? Very big. Maybe you can optimize this kind of structure. And the end, some algorithms to fine tuning use this kind of approach, okay? Because the matrices of transformers are very big. Maybe you can use that approach to knowledge distillation, but in the training process, okay? You can use the knowledge distillation, you know, when you have the model is training, but the idea maybe is to use this kind of approaches during the training, okay? To produce, you know, a more optimized architecture. This is a point that is possible to see, okay? But this is an open question, okay? A lot of people is working in how to improve the transformers. You can see some papers, for example, I don't know, several months ago, arise a paper with a new architecture, Mamba. Mamba is a kind of using a state model, something like that, a state model. This is a kind of architecture that the community of deep learning is you know is proving to maybe to improve the transformer. Okay.
Okay, super. And again, you will find all the slides on the website. So
Yes. All
if
right.
you want to get back to Jesus for any questions, you can do that. Okay, thank you very much.
No, thank you. Thank you to everyone.
Thank you.
Thank you
Jesus.
again for the invitation, Marco. Very nice.
Thanks for the fantastic presentation.